So moving it up, we can think about a little bit about how we're going to make this light and use it. So if we take visible light, we know how to make that. We make that with hot wire, for example. And our hot wire is going to give out all kinds of light. If we go down to infrared, we can think about also using a hot wire, but it doesn't need to be so hot. That has a lot of advantages, because if we take an old style light bulb, which probably none of you have very much experience of, but if we take an old style light bulb, they don't last very long. If we take an infrared source, it just has to be a bar of something that conducts electricity, and we pass some current through it. It gets warm. It'll give out infrared of all kinds of colors. So that's easy to make. Hot rod. Let's call it a hot rod. Whoops. Making ultraviolet is a little bit more difficult. We need some kind of, because a hot wire is not going to cut it. Why is that? As you know from physics, if we heat something up, it will give out blackbody radiation. And blackbody radiation has a Boltzmann distribution, which you all know. So if we draw a Boltzmann distribution like this, this will be what we would expect to see if we heat something up. So this is our energy of light going up here. So we could do it by frequency. We can't do it by wavelength because it's the other way. This is how many photons we get back out, so let's call it number, and this is our energy. Let's call it E for energy. And we see that there's a peak and it goes down very quickly afterwards, but it carries on for a long way, so we get high energy photons out. But if we heat up our wire even more, it shifts the peak a little bit, but we would have to heat it up extremely much to get it to go into the ultraviolet region, and we still wouldn't get very much ultraviolet light out. We can do that. We have to use a special bulb that will go into the ultraviolet region a little bit, and then we run out of ability to make it just by heating things, because we run out of materials that don't melt at that temperature. So as you know, the brightest bulbs are xenon or halogen bulbs, so we would have a xenon bulb here, xenon hot wire. And then to make even more ultraviolet, we'll have to use, we'll have to excite some molecules directly. We'll have to use a different way. Now, so we'll come on to that when we do that. Then we have X-rays, which we spoke about before, which are generally created by having an electron and accelerating it to a high speed and then crashing it into something. And we usually use a metal for that, firstly because the metal will cause it to release low energy X-rays, but also if we want a single color of X-rays, we have to put a lot of electrons in. It will get really hot, and it's handy to have a metal because it's easier to cool practically. We'll get also single colors of X-rays out when we shoot out an electron from the core of one of the atoms in here. So it could be a block of a magnesium, could be a piece of aluminium. We shoot out one of the electrons, and then another one falls in from the conduction band of the metal. So now we've made it, we need to manipulate it and also measure it. So here, let's start in the visible region, because we're probably all more familiar with that. If we want to manipulate it, we can use a lens, glass maybe, or polymer. I would write plastic, but it's a materials science course, so it would be bad to use the wrong word. Polymer is correct. Plastic is not the right name for it. If we go down to infrared, we have a problem. The problem is most things, like glass for example, absorb infrared quite effectively, and so we need other substances to let it through. We can still use lenses, but the lens will be made of other things, so the lens will have to be made of a substance that lets infrared through. It depends where on the spectrum we want to look at it, but the lens will typically be made out of an ionic substance, because an ionic substance doesn't have any of the bonds in it that would be absorbing the energy. So let's say cesium bromide is a typical one. There's a problem with that, because cesium bromide or sodium chloride or potassium chloride, whatever we want to use to make it out of, will tend to absorb water from the air and turn into salty water. So we typically don't use very complicated lenses in infrared. We can also use mirrors. That's better. Mirrors will reflect the infrared. We might want to, if we need any other optical components, we will have to make them out of an ionic compound or out of a semiconductor where the band gap is such that it can't absorb the infrared very easily. So depending on what it is, silicon is sometimes quite useful. Gallium is also, germanium is also used quite often. If we move up to the ultraviolet region, we have the same problem the other way round. Glass is not very good for passing ultraviolet, and so we now need special components for it as well. If we go up to quartz, which is just a different crystal structure, or it is a crystal structure, it's the crystal form of silicon dioxide, and it's a more pure form. It can pass ultraviolet up to a very high wavelength, actually, very short wavelength actually. So it's a very good lens for ultraviolet, and obviously mirrors are also useful. But there is a problem. There's a problem at both ends. So what we can think about is, if we take a mirror, if we take a lens, it's slightly different, but if we take a mirror, we're going to interact with scratches on the surface, and the surface can never be perfect. And the question is obviously, how perfect is perfect enough? So if we take visible light and we make scratches on it that are smaller and smaller and smaller, eventually we won't be able to see them because the individual wave of visible light is too big to be affected by the scratch. If we take the same logic, it is easier to make a mirror or a lens for infrared because all of the structures are bigger. It's easier to fabricate these. It's harder to make ultraviolet components because they have to be very smooth indeed. Otherwise they're going to scatter the ultraviolet light and cause a problem. X-rays are of course even worse, because X-rays will pass through most things. What we know about X-rays is they will interact with crystal structures, and so if we take a crystal and deform it, the X-rays will interact with the crystal and be modified in a way. So we need a crystal. We have effectively the opposite problem that we had with ultraviolet and infrared. With ultraviolet and infrared, the problem is that that very many of the materials we would like to use absorb the light, but in this case it passes through most of the materials that we would like to use. And now we would like to detect them. So if we look invisible, you will be familiar with taking pictures with your phone. Where is my phone? I've left it somewhere lying around. That's interesting. Or this camera that I'm using, which is a webcam. If we take images using that, we're using what's known as a CCD, a charge coupled device. So we're using a semiconductor, and the semiconductor is absorbing the light and giving out, in that case, some current, and the current's measured by the camera in some way and used to form an image. So this would be a semiconductor. We have electrons. In the case of a charge-coupled device, it's a cascade, so we've got some electrons in a high energy state. When it gets hit by a photon, it gives out some current. This is much the same. Infrared is similar. We can use a charge-coupled device to detect actually ultraviolet light and infrared reasonably well. But for the longer range infrared, we have a problem. So the near infrared, okay, we can use pretty much a normal camera. It can see further into infrared than we can. But if we want to detect the interesting part, where the chemical bonds interact, then we have two problems. Firstly, we're limited to the materials we can put in front of it. So most cameras wouldn't work because they've got some kind of polymer or glass in between, and so it would stop working. But also, there isn't enough energy in the photon to do the process that happens here, to kick an electron out of a well and allow the current to flow. But the process is very similar. So what do we have? We have a semiconductor. So we've got some there are electrons down here, and this would be the conducting band. Whoops, I've drawn it smaller. That's weird. So we've got some electrons down here, and if we hit it with an infrared photon, it will excite an electron, one electron, into the conduction band. So just trying to keep the same as organic chemistry, we're going to draw one-armed arrows for one electron moving, two-armed arrows for two electrons moving, so that we've got a consistent terminology inside chemistry. It's not always done like that, but I like to keep it lightweight. So we're going to have a single electron being kicked from the conduction band of the semiconductor into the from the bonding band of the semiconductor into the conduction band. That would in a normal case just sort of float around and fall back down again, or immediately fall back down into the hole that's generated. So let's resolve that. We would have a positive hole and a negative electron floating around. To make that more useful, we should make this negative and this one positive, and that will help. So effectively we are attaching our let's connect it all, because that would be silly. So we connect this end to a negative terminal and this end to a positive terminal, and we need to measure the current somehow with an ammeter. It's obviously got to be really sensitive. When we do that, because the electron is negatively charged, it will move in this direction, and the hole is positively charged, it will move in this direction, and we will separate the electron and the hole, and that will enable us to measure the current from each photon that comes. There is a problem, obviously. If we get a high energy photon coming, it could release several electrons. We have to work out a way of counting that. Typically our device will separate the infrared in time. So we have to get different wavelengths at different times, or we could separate it like our camera in space. So in our camera, the different colors of light are absorbed by different pixels, and they're separated by some kind of optics depending on how the camera works. Different cameras have different ways, but they usually just have a colored screen over each pixel to prevent the wrong colors of light going in there. It's not a very efficient way of doing it, but that's how it's done. If we want to measure ultraviolet, it's actually not very hard. We can use the same technology as we did here. The problem is much the same, that we need to split the ultraviolet into different colors, and that's very difficult because it's short wavelength. If we get into X-rays, we have a new problem. The new problem is the X-ray has a lot of energy and it goes through most things. We also need to convert it into an electron somehow or into something that we can measure. And the easiest way to do that is similar to the charge coupled device. We allow it to hit a charged screen. It will release electrons. So we can use the process that we're going to measure anyway. So when it hits a material, it will release electrons, and we can count those electrons in a similar way to this, in fact. So it hits, releases electrons. We can count the electrons. We will come on to that when we get there. Where are we? X-rays. So in X-rays, we can either do much the same as we would do here, split the light into different colors. It's a bit difficult because we need a crystal to split it, so it costs a lot of money to do it. We have to generate a crystal that's distorted in a special way so that we can split the X-rays into different energies, effectively colors of X-rays, and we can then measure them separately. Or we can measure the energy of the X-rays all at the same time. That has a different problem. We use a semiconductor to do that, much like the one here, but instead of measuring a one electron process, we hit it with an X-ray, which gives it a lot of energy. It shoots out a lot of electrons, and we can count those. That has problems because it is a little bit difficult. It's not impossible, but it's a little bit difficult to determine whether you get one photon hitting our detector and releasing a whole load of electrons, or two come at the same time. How do you work out when that happens? You obviously have to turn down your X-ray source so that you're only getting single events, and you can keep them apart. It matters obviously how quickly you can get the electrons out and count them. And the more modern ones are very fast, and therefore they can have a comparatively high count rate, but it is difficult.